Chapter 4 Surface Tension and Capillarity. Now we are going to discuss about one of the peculiar and very interesting nature of fluid, that is surface tension. In this portion we will detail about surface tension and capillarity. When a fluid comes in contact with another gas or immiscible fluid, then the contact surface in between the two fluids acts like a membrane under tension. This phenomena is called surface tension. To understand the surface tension, let us see a video.
Surface tension, in which we will look at how intermolecular forces affect the surface of a liquid. So what is going on at the surface of a liquid? Let's take a look by shrinking to the nanoscale. So here we are looking at the individual molecules in a liquid, and let's say that each blue circle represents a molecule of water. Due to kinetic energy, the particles that make up a liquid are in constant random motion, and so they will have a random arrangement. You might expect the particles at the surface at the micro level to form a random surface as shown here. But what we should find out is how do intermolecular attractions influence the surface. First, let's look at intermolecular forces under the surface, where attractions of individual molecules pull on each other in all directions. At the surface, pull on the molecules is lateral and downward. There is negligible attractions above the molecules, and so the net force on surface molecules is downward. The result of this downward force is that surface particles are pulled down until counterbalanced by the compression resistance of the liquid. Surface molecules are compressed more tightly together at the surface, forming a sort of skin on the surface with less distance between them compared to the molecules below them. Surface molecules also form a much smoother surface than one would expect from randomly moving molecules. What do you think surface tension would do to a liquid not confined in a container? In this model of a small water droplet, what is the net direction of the force on the surface molecules? That's right, it is toward the center. And so a free-falling drop of liquid takes on a spherical shape. Here we see water dripping from a faucet. If this does not look familiar to you, turn on your faucet at home with very little pressure and see what happens. Or do an internet search for the behavior of water in zero gravity to get a great view of surface tension.
The molecules on the middle has a force of attraction in all direction, hence no resultant force will be there. However, the molecules on the surface will experience a net downward force because it is surrounded by neighboring water molecules only on one direction, not in upward direction. Hence a net resultant downward force will be there. So due to this downward force, the molecules on the surface get closely packed and the surface of the liquid acts like a thin film under tension. This is called surface tension. Now we are going to estimate the surface tension force that acts on different surfaces. Initially we take the case of a liquid droplet. Liquid droplet is a hollow body, that is a spherical body with air inside surrounded by a membrane of liquid. Let us consider a liquid droplet of radius r, diameter d and surface tension b sigma. When the droplet is in the state of equilibrium, the surface tension force that acts on the surface of the droplet compensates with the pressure force inside the droplet due to the presence of air inside. Hence we can equate both the forces. Now we are going to estimate the entire tensile force acts on the surface due to surface tension. Sigma be the surface tension, then the entire tensile force is equal to sigma into circumference, because the surface tension acts only through the circumference of the liquid droplet. That is equal to sigma into pi into d. Now we have to estimate the pressure force inside the droplet. Pressure force acts through the entire cross section of the droplet, that is the entire area of cross section of the droplet. Let P be the pressure intensity, then the pressure force is equal to cross sectional area into P. Area of the droplet, we know that it is pi by 4 d square. So the pressure force becomes pi by 4 d square into P. Equating the total tensile force and the pressure force, we get sigma into pi into d is equal to pi by 4 d square into P. Upon rearranging the equation and cancelling out the similar terms on both sides, we get the equation pressure intensity inside the droplet P is equal to 4 sigma by d. The diameter comes in the denominator. Hence, if the diameter of the droplet decreases, then the pressure intensity inside the liquid droplet increases. Now let us discuss about capillarity. Capillarity is yet another interesting feature of fluid. Capillarity is defined as the phenomena of rise or fall of a liquid inside a small tube relative to the container in which the tube is held. That is, if we immerse a small tube inside a container containing water, then the level of water inside the tube will rise up with respect to the level of the water in the container. This is because of the reason that the force of attraction between the water and glass molecule becomes more than the force of attraction within the water molecule. If we place two water molecule and a glass molecule together, then the water molecule will get attracted towards the glass molecule, overcoming the force of attraction within the water molecule. As a result, if we place a tube in a container, then the water level inside the tube will rise with respect to the water level inside the container. The glass molecule attracts the water molecules and overcome the force of attraction within the water molecules. Daily life example. Absorption of water by a sponge against gravity is due to capillary action. If we place the water there in the floor, if we place a sponge over the water there in the floor, then the water gets absorbed into the sponge. This is actually against the law of gravity. This occurs due to capillary action. Plants absorb water from the soil also by this capillary action. You may have wondered how the water reaches all the way top of a coconut tree while traveling all the distance against gravity. This process takes place due to capillary action. Now we are going to formulate an equation for capillary rise. The surface of the liquid on the tube is not actually flat, whereas it is actually a curved concave surface as shown below. This is because the water molecules on the top are well arranged due to surface tension like pebbles on a chain, and these glass molecules pull these water molecules in the upward direction. How this concave surface is formed? This concept can be understood by taking the example of a jumping net, person in a jumping net. When person falls on a jumping net, the jumping net is stretched all around its circumference and weight of the body of the person acts on downward direction. As a result, a concave surface is formed on the net. Likewise, the surface tension acts only through the circumference of a glass tube, whereas the weight of the entire water column acts through the entire cross-sectional area. Hence, a concave surface of water is formed on the top. Surface tension sigma acts as an angle theta with vertical. Hence, we equate the vertical component of the surface tension with weight of the column with height h. Weight of the column is equal to the volume of the water column into mass density rho into g. Volume we can calculate by taking the product of area and height. Hence, the weight of the water column will become pi d square, that is the area, into a height h into rho into g, where rho is the mass density. Equating the weight of the column with surface tension force. Surface tension force is acting at an angle. Let us consider the picture in which the surface tension force is acting at an angle theta all around its circumference. So, we can equate the vertical component of surface tension force with weight of the column. The vertical component of the surface tension force is equal to sigma into circumference into cos theta. That is equal to sigma into pi d into cos theta. Equating both the weight of the column and surface tension force, we get the equation sigma into pi d cos theta is equal to pi d square h into rho into g, where the first component is the surface tension force acting on the vertical direction. Second component is the weight of the liquid column acting on the downward direction. Upon rearranging, the equation becomes h is equal to 4 sigma cos theta by rho into g into d. The value of theta between water and glass is almost 0 because surface tension acts almost vertical in the case of glass and water. Therefore, the value of cos theta is near to unity. Hence, the equation becomes the height of rise h is equal to 4 into sigma by rho into g into d.